The universe is such an amazing place, with a lot of different heavenly bodies in it, from planets, stars, and galaxies to black holes. A common property that most of these cosmic bodies have is that they are round or spherical in shape. So, what could be the reason for this? What are the forces in the universe that shape so many of its objects into spheres? In this video, we're going to talk about why are so many objects in the universe round. We will uncover the gravitational force, fluid dynamics, and the principles of formation and evolution that govern celestial objects. The heavenly bodies, such as planets, stars, and galaxies, are all kinds of objects in the universe that are round, but not in the same way. Whether small as cosmic dust or as big as galaxies, the diversity among celestial bodies is simply mind-blowing. On the other hand, there is a commonality among many of the objects, which is that many of them are round. The round planets, round moons, and round stars exhibit roundness or near roundness. It may be just a mere coincidence, but it is not that at all. The fact that these celestial bodies are round is due to the basic laws of physics, which determine the evolution of the universe. The matter which arises now is this: why is so much of the universe's matter shaped like a ball? This video wants to find a solution to the problem through a discussion on the role of gravity, the idea of hydrostatic equilibrium, and how size, mass, and rotation are the main elements for determining the shape of celestial bodies. We will also study the non-brilliant nature of some objects by tracing asteroids and other small objects that resist the force of gravity, causing them to be distorted. The knowledge of these principles will help us to understand the processes that have not only brought about the transformation of our planet, but of the entire universe. Everything in the universe is governed by the great law of gravity. It is the force of attraction that attracts the mass towards the center of gravity, thus influencing the objects that are both large and small in mass. Gravity acts equally in all directions, which means that every particle of a celestial body is attracted to the center of the body. The reason that gravity attracts all things in the same way is that it prefers spherical shapes. More massive celestial bodies, such as stars and planets, gravity becomes the dominant force. That determines their shape. The gravity that draws the material towards the center is the reason for the object to be spherical, as it is the most efficient way to distribute the mass under the gravitational pull. The smaller ones, such as boulders and asteroids, may not be affected by their material strength, but the larger ones will eventually be changed by gravity's shaping force. A sphere is a shape that, by minimizing the potential energy of the object, in effect, represents the most stable form for a self-gravitating object. So, gravity is the reason behaviors not only come together, but also get molded into the shape of a sphere in the process of obtaining a stable state. Hence, gigantic cosmic bodies, for example, planets, stars, and moons, can be cited as two examples. The reason for their spheroidal shape: they come to a point where the forces at play within are balanced, a concept of hydrostatic equilibrium. Hydrostatic equilibrium is a state that happens if gravity's inward pull and the outer pressure of the material inside an object are exactly equal. The balance of forces thus creates the spheres, because the sphere has the ability to distribute the forces equally in all directions. In other words, if you think of a planet or a star, every part of it is being pulled in by gravity, but at the same time, the internal pressure due to gases, liquids, or solids is pushing out. When these forces are in a stable equilibrium, the outcome is a perfectly round shape of stars. This equilibrium is kept due to the nuclear fusion in the core, which produces a huge amount of heat and pressure that push outward against the force of gravity that pulls inward. This careful draining ensures that the star is not crushed under its own weight. Likewise, the solar and Earth systems include planets and moons where hydrostatic equilibrium is also the condition, yet the forces are different. Planets, for example, may have a molten core that generates a pressure pushing outward, but gravity is pulling solid material inward. Thus, a round shape is stable. Hydrostatic equilibrium is the most important being. It is what keeps the celestial bodies stable for billions of years and is the reason for its importance. Take away this balance, and stars would collapse, planets would deform, and the universe would be a very different place from the one we see today. This equilibrium is the reason why star-like objects above a certain size and mass will always tend to a spherical shape, since it is the only configuration that can balance these opposing forces. If gravity always tries to make objects round, how come celestial bodies aren't all spherical? The answer to the question lies in the size and mass of the object. Little objects, such as asteroids, comets, and some moons, are not heavy enough to have gravity overpower the other forces, the ones that are made of rigid material. These material forces are the ones that mainly kept the object shaped like it is. In smaller celestial bodies, the strength that is given by rock or ice can counter the pull of gravity, preventing the object from collapsing into a round shape. Sometimes, asteroids are very irregular in their shapes, and they are not round because the gravity pull of these celestial bodies is too weak to make them spherical. The chemical bonds and the physical structure of the rock or ice that they are made of are, in fact, stronger than the force of gravity, which tries to bring them together. Thus, they hold on to their peculiar forms, unless they become so big that their gravity forces are no longer negligible. As soon as an object becomes norm, it should become bulky enough so that its mass becomes an overpowering force for the internal repulsing of the material. The critical point at which this occurs is referred to as a potato radius, which is about 200–400 kilometers in diameter. This is true for the growth of any celestial body as long as it is not too small, which would bring its strength down to the point where it cannot be deformed by the lightest force. Up to this point, objects will almost remain undeformed and be in a state of collision, or the strength of their materials will be the main reason to give them a shape. Elliptical orbits are common due to the mass of a celestial body exerted on them. However, they do not always have to be round. It's the case with planets and stars, in which they don't all have a spherical shape because of their rotation, which distorts their shape. The rotating object pushes some material outside the center of rotation, hence forcing the solid body to bulge. This D-shape phenomenon, where the object is flattened at the poles and bulging out at the equator, is known as oblateness. A great example of this is Earth. Despite the fact that it appears circular from space, it is actually an oblate spheroid. Because of its rotation, the equator is approximately 21 kilometers wider than the poles. And add that the faster an object spins, the more the effect will be. Among the gas giants, Jupiter and Saturn are the ones that rotate fastest, and hence the bulges of their equators are even more noticeable. The flying telescope will even distinguish Jupiter as an oblate plane when it has a big bulge around the equator. This can be seen in the stars. The stars that are in rapid motion make even stars to have noticeable variation in the shape. Such cases of a star's rotation reaching such a speed that the centrifugal force nearly balances the inward pull of gravity, thus the star's equatorial bulge appears to be prominent or extreme, are extreme. The interplay between the forces of gravity and rotation contributes to the variety of shapes that celestial bodies can assume. Thus it is shown that, although round shapes are typical, there are cases when the shape is not round perfectly. Fluid is a common state for celestial bodies, not only solid. For instance, gas giants, which are mainly made of fluids, and stars, which are mainly made of solid, are the ones that are formed from materials that behave like fluids. Even rocky planets, such as Earth, can show a fluid-like behavior if the long-term timescales and gravity and internal forces effects are considered. The fluid dynamics phenomenon is crucial in shaping such bodies into a sphere. On the other hand, for stars, fluid dynamics is of paramount importance because most stars are made up of plasma, which is a state of matter that is composed of ionized gas. The plasma, which is a more fluid-like substance than solids, allows gravity to easily format stars into spherical shapes. Furthermore, as stars are always performing nuclear fusion that exerts a gigantic pressure outward, they are able to keep their shape by the interplay between the inward pull of inertia and the outward pressure of the gas. In fact, planets can have a hard surface, but under extreme levels of pressure, the interiors can act as liquids. Long enough time really makes rock behave like liquid, and that is why giant planets can become fully rounded. Planets composed mainly of hydrogen and helium are essentially gas giants, such as Jupiter and Saturn. These planets come near to being perfect spheres, yet because of their rapid rotation, there is a little bulging effect at the equator. Therefore, fluid dynamics is a major factor in keeping celestial bodies like the Earth in spherical form, while their insides remain quite complex. Among the cosmos, galaxies are the biggest formations, and although they include planets and stars, their spherical shape does not follow. On the contrary, galaxies have many different forms, ranging from a spiral, an elliptical, to even an irregular one. This variation is due to the fundamental properties of galaxies. In fact, a galaxy is a dense aggregation of stars, gas, dust, and dark matter, all held together by gravity's force. Mercury, the mother of all mazes, is one of the spiral types with a flat disc-like outline and a dense core that has a pair of swirling arms around it. The consequence is the shape of the angular momentum of the material included within the galaxy, which causes the disk to rotate. Gas and stars found in a galaxy move in circular orbits, and as a result, we observe the spiral structure. In contrast, elliptical galaxies are more rounded and are not that perfect close to the spherical form. As a matter of fact, the occurrence of these galaxies is when two or more smaller objects of the same galaxy come in contact and the distribution of the stars becomes random. Dark matter is an invisible thing that is a major component of the Earth's mass and is a very important factor in the formation of galaxies. The construction of dark matter gravitational wells creates a situation where the attraction of regular matter occurs, and this is the overall structure of galaxies. Although dark matter is not visible in itself, its gravitational effects give a good explanation of why galaxies are grouped in certain regions of space and why they have specific shapes. Among the farthest reaches of the universe, one would find two most extreme objects, namely black holes and neutron stars, that have their own shape owing to the influence of the significant gravitational forces that they are under. Black holes, for instance, are where very heavy gravitational forces pull everything so much that even light cannot escape them. Event horizon, which denotes the boundary beyond which nothing can escape a black hole, is a spherical formation, while the singularity at its center is still a point of infinite density. The above phenomenon lawfully happens because when gravity becomes very strong to the level of trapping everything that dares come close to the black hole, then a perfect sphere is created around the black hole. Neutron stars are collections of particles that are left behind as the remains of the giant dead stars that have long gone through the supernova explosions. These are some of the dumbest objects in the universe, having mass equal to the Sun, yet they are confined to a volume of only a few kilometers. Neutron stars are mostly spherical, but their shape can change slightly to ablate, just like the planets, if they move really fast. In a few instances, neutron stars behave normally, but other times, they have super strong magnetic fields that can tilt their bulge more than usual. The study of these peculiar objects shows how gravity, in conjunction with the rest of the forces, can yield to both rounded encasements and the like. Finally, the roundness seen in so many objects of the universe is not an accident at all. Gravity, the force that plays a major role in the shape of celestial bodies, naturally prefers the spherical form because it is the most efficient way to distribute mass and balance forces. The spherical shape of the planets, stars, and even black holes is the result of the basic laws of physics. Nonetheless, the joy of souls gravitating towards spheres is still reflected in the deviation of other forces such as rotation, fluid dynamics, and internal structure that can create slight imperfections. These factors give complexity to the shapes of the universe, but the main trend is clear. The roundness is the natural result of the forces controlling the cosmos. Grasping the reason behind the roundness of so many objects in the universe enables us to understand the evolution processes behind our planet as well as the whole universe. It is through viewing the universe as a delicate balance of forces that we can appreciate the beauty of the intricate system that it is shaped into. Thanks for watching this video.